Welcome everybody to our second video in our series on cross products. Today we'll be talking about the properties of the cross product operation. So just as a reminder, if we were given two vectors, so suppose we were given a vector u being u1, u2, and u3, and we were given another vector v with components v1, v2, and v3. Well, in order to compute the cross product, remember that will give us a new vector, and that new vector is going to have components of the form. So for our first component, it will be u2 times v3 minus u3 times v2. For our second component, we have an alternating sign, so we have a negative, then a u1 times v3 minus a u3 times v1. And then finally, for our third component, we have a u1 v2 minus a u2 times v1. And remember what this was supposed to give us, that for our vectors u and v, that the cross product, or at least the magnitude of the cross product, was really going to give us the area of that parallelogram formed with sides u and v. And furthermore, if we knew that the angle between those two vectors was going to be theta, then this was going to give us a value that was the length of u times the length of v times the sine of the angle in between. So the first property that we encounter is the fact that cross products are anti-commutative. So what we really mean when we say that something has the commutative property, so kind of the best example of that we've just encountered is really our dot product. So that if we do the dot product of u and v, it really doesn't matter which order that we do those dot products in. We're going to get the same answer either way. Well, with anti-commutativity, what happens is that if we do the cross product in the opposite order, so that if we would, instead of u cross v, we did something like v cross u, we don't get the same answer. The answer that we get is actually the negative of the answer that we had in the with the other order. So the commutative property, order doesn't matter, so u dot v is v dot u. Anti-commutativity introduces a negative if we switch the order. So u cross v is equal to negative v cross u. Our next property that the cross products satisfy is the distributive property. So what this means is that if basically the cross product respects our property of scalar multiplication, so that if we were adding two vectors together, so if we had something like our u plus v, and then we took the cross product with w, well, that cross product is going to distribute just like with our usual multiplication and addition, so that we have u cross w plus now v cross w. And that actually holds with both components. So it can be hold in if we're adding in the first component, but it can also hold if we're adding in the second component. So if we did u cross v plus w, that's still going to give us a u cross v plus a u cross w. So our third property that cross products have is that it respects our scalar multiplication. So that if we had a scalar alpha times a vector v, and then we took the cross product with w, well, we can essentially factor that scalar out. And so this is going to be our scalar alpha times our v cross w. And it also holds for the second component. This is going to be equal to V cross alpha times W. And for the next property, property 4, it kind of goes without saying, but if we would do the cross product with the vector of all zeros, then we get the vector of all zeros. And it really doesn't matter whether we do u cross 0 or whether we do 0 cross u, we're going to always get an answer of 0. For our fifth property, this one is more of an identity property that if we did the cross product of a vector with itself, then this is always going to return us the 0 vector. Another very important property that we have with the cross products, and that we'll use over and over and over again, is the fact that if we do the cross product of a vector with another vector, so u crossed with v, then that new vector u cross v will be orthogonal to both u and v. So basically we have a picture that's kind of doing something like this. We have a vector u and we have a vector v. And then if we take the cross product of those two vectors, so we have a u cross a v, then that new vector u cross v will actually be perpendicular to both our vector u and our vector v from our original. To see that that's actually going to be the case, we can just do something simple like if we did the dot product with u cross v. Well, that dot product is going to be the dot product of u with our new vector u2 v3 minus u3 v2, a negative u1 v3 minus u3 v1, and then a u1 v2 minus a u2 v1. If we dotted that with u, what we end up with then is a u1 times a u2 v3 minus a u3 v2 plus, or rather minus, because our second component is going to be negative, so a minus u2 times a u1 v3 minus a u3 v1, and then finally a u3 times a u1 v2 minus a u2 v1. Well, if we go ahead and distribute all of those, we have a u1 u2 v3 minus a u1 u3 v2. Then we have a minus u1 u2 v3, and then a plus u2 u3 v1. And finally, we have a u1 u3 v2 minus a u2 u3 v1. Well, now what happens when we kind of examine these things, our u1 u2 v3 cancels with our u1 u2 v3. Likewise, our u1 u3 v2 cancels with our u1 u3 v2. And lastly, our u2 u3 v1 cancels with our u2 u3 v1. Sure enough, in fact, giving us a value of 0. And so since the dot product with the vector is 0, that means that u is going to be orthogonal to v. If we did the same calculation with v, we would see that sure enough our terms cancel, and that v is going to be orthogonal to u cross v as well. Now this has some bearing in the next property that we're going to see, the new property called the scalar triple product. Now, what the setup for this one is, suppose we have three vectors. We have a vector u, and then we have a vector v that's headed off in this direction, and finally we have another vector w that's headed off in that direction. Well, if we form a three-dimensional object from these three vectors, then we get a geometric object called a parallel pipe. And so what this thing, the significance for this geometric object, is that the volume of this parallel pipe is actually going to be the scalar triple product of W dotted with U cross V. Now, to see where this really comes from, if we think about the product the property that we just saw, namely that our cross product of u and v is going to be perpendicular, it's going to be orthogonal to both u and v. And so if we want to kind of think of the height of this object, we know that the area of the base is going to be given by just the length of that cross product. And so if we knew that the area of that base, and then if we had the height on it, then we would actually say that the volume was going to be equal to just the area of the base times the height. Well, how do we get the height of that thing? Well, therein comes our orthogonality property. So we have a vector, so our vector u cross w is actually going to be perpendicular to both u and v. And so what we can kind of think of then is the magnitude then of kind of that height is really going to be equal to kind of the scalar projection of our vector w onto our cross product vector u cross v. So that our height, if we would draw the perpendicular over to our vector w, then the height that we are looking at is really just, again, coming from our definitions from trigonometry, that the height of that object is really just going to be the length of w times the cosine of the angle in between our normal vector, our vector u cross v, and our vector w. So our angle theta now is the angle between our vector u cross v and our vector w. And so what happens then with this, if we look at v dot u cross v, what we then have, w dot u cross v is going to be equal to the length of w, the length of w times the length of u cross v times the cosine of the angle in between. Well, our length of w times the cosine of the angle is the height. Then the length of u cross v is the area of our base. And so sure enough, the volume for this parallel pipe is given by this scalar triple product. And so that kind of gives you a little bit of motivation for where this property is actually coming from. And so kind of summing up all of the properties that we've discussed so far, we have them all kind of listed here in this box, with the exception of one of our other important properties, and namely that u cross v is orthogonal to both u and v. So those are all of our properties listed, and what we can do with those properties then is kind of give us a purely algebraic way of computing the cross product in terms of our basis vectors of I, j, and k. We have our vectors I having components 1, 0, 0, our vector j having components 0, 1, 0, and our vector k having components 0, 0, 1. Well, a straightforward calculation just shows that if we do I cross j, then that's going to give us 1, 0, 0 cross 0, 1, 0. And so this will be our second component times our third component minus our third component times our second component. And so we have a component of 0. Our first times our third times our first, also giving us a 0. And then finally, our first times our second, giving us a 1, and then minus a second times our first, also giving us a 0. And so sure enough, we end up with 0, 0, 1, or we have our value of k. If we go through, then can compute the others, what we notice is a pattern that if we do j cross k, that will in turn give us a 1, 0, 0, or an I. And if we did k cross I, that will give us a value of 0, 1, 0, or our j. And so this kind of gives us a shortcut in a way for our what we call a cyclic permutation of our I, j's, and k's. So if we start with the first one of just I, j equal to k in our kind of alphabetic order, then if we imagine doing a shift on those vectors. So a shift being our j vector comes over, our k vector comes over, and our I vector then wraps around to become I on that side. And so this gives us our second component. If we cycle through one more time, we get our third component. So if we cycle again, then we have k moving over to the j spot. We have I moving over to the k spot. And then we have j wrapping around to the equal side spot. And so this gives us kind of we do call this a cycle for our vectors I, j, and k. So we have our I, our j, and our k values. So our cyclic permutations. But then also from one of our properties, we have that our vectors, that if we switch the order of those, it introduces a negative sign. And so if we know that I cross j gives us k, then we know that j cross I is going to give us a minus k. And likewise, if we know that j cross k gives us I, then k cross j is going to give us a minus I. And finally, if k cross I gives us j, then I cross k is going to give us a negative j. And finally, our last property that we have was that if we took the cross product of a vector with itself, then we ended up with 0. And so that gives us, if we have an I cross I, that will give us the same value as if we did j cross j, and that gives us the same value as if we did k cross k, namely that gives us the 0 vector. And to see how we can kind of compute our cross products algebraically now, let's take a concrete example. So suppose we had two vectors. We had a vector u that was going to be 2I plus 3j, and we had a vector v that was going to be a minus 4j plus 5k. If we wanted to compute the cross product of u and v, then we're really taking the cross product of 2I plus 3j cross a minus 4j plus 5k. Well, according to our distributive property, what we can do is to take this minus 4j plus 5k, and it will distribute to each of the vectors across that sum. And so what we then have will be a 2I cross a minus 4j plus 5k, and then a plus 3j cross a minus 4j plus 5k. All right, so now we distributed once, then we can distribute again. So we can distribute our 2i, and we can distribute our 3j. So what this will give us are values of 2i cross a minus 4j plus a 2i cross a 5k, and then plus a 3j cross a minus 4j plus a 3j cross a 5k. Well, now with our scalars, we can just pull our scalars to the outside. And so what this is going to give us is 4 times 2, a minus 8, I cross j, plus a 10, I cross k, and finally a minus 12, j cross j, and plus a 15, j cross k. Well, now using our properties immediately, that if we cross a vector with itself, that would become 0. We lose our j cross j term, so that one goes away. And so now for our remaining vectors, we can use our kind of cyclic properties that we had. And just kind of remind us of what those were. Well, if we had I cross j, that was k. If we had j cross k, that was I. And then if we had k cross I, that one was j. And so with these properties, if we switch any of those orders, remember now that changes the sign. And so what we then have is our I cross j becomes a minus 8k. Our I cross k, well, that's the negative of k cross I, so that becomes a minus 10j. And j cross k gives us I, so we have a plus 15 times I. And so what do we have as our vector for u cross v? We have the vector 15, negative 10, and negative 8. And so kind of using our cross products of our i's, j's, and k's together with our distributive properties, then we can kind of compute our cross products purely algebraically without kind of appealing back to our formula that once we've done it for the basis vectors for I, j, and k, we have the values for everything else in hand. So this kind of takes us through all of our properties of our cross products. So now we're able to kind of turn over and start looking at some of our concrete problems. I will see you guys in the next video.